All right, so now what we'd like to do is see what those coefficients need to be so that we have a power series where for some given function at some point, right? Remember, a is some value of the function. We'd like the series to equal the function at that point, the first derivative to equal the first derivative of the function at that point, second derivative, third derivative, and so on. So we're going to be able to differentiate this. Remember, we talked about the term-by-term differentiation theorem for power series. That's going to come in handy here. We're going to just go through a few derivatives, and a pattern is going to emerge, and we'll see if we can spot that pattern. So I'm going to avoid the sigma notation. I think when it comes to going through this and recognizing what's happening, it's probably easier to just write out some terms. So first, let's go for that first thing. We want S at A to equal F at A. So first one we're going for here is we want S at A to equal F at A. So first of all, what's S of X? Writing out just what a power series looks like, right? A power series is like this. And we would like S at A to equal F at A. So what has to be true for this to happen? Well, let's plug in A. Well, and now you can see why we center this at the point we're interested in. Because when you plug in A, everything goes away, and all you have is C naught. And we want S of A to equal F at A. And so in order for that to be true, that first coefficient, C naught, must be F of A. So 1 down, infinity minus 1 to go. We just got to get all those coefficients. Luckily, a pattern will arise pretty quickly. But notice that was the first coefficient in our linearization, if you remember L of x. So far, we're matching the linearization. So let's go to the next. Let's take a derivative. We want S prime at A to equal F prime at A. So we'll use our term-by-term differentiation theorem. What's S prime of x? Well, C1 plus 2C2 x minus A. And because everything goes down a degree, I'm going to have to bring in another term. I'll just stop at the second degree each time. And just the next one would have been the cubic, where the 3 came down. So what's S prime at A? Well, again, all the things beyond 0 degree go away. And you just get C1. Well, what did we want? We wanted S prime at A to be F prime at A. So in order for that to be true, C1 must be F prime at A. So now we've got the first 2 coefficients of what that power series should look like. And again, recall the linearization. Actually, those were the coefficients on that linearization, L of x. So far, all we've done is recreate the linearization if we just stop there. So now, let's move on to second derivative. So we want S double prime at A to equal F double prime at A. What's S double prime of x? Well, term-by-term differentiation. We just differentiate that. We'll have the 2C2. That 2 will come down. And when you're looking for patterns that are generated by some process, it's often nice to not simplify because you can see how the numbers are being built up. So I'm not going to write that as 6 when the 2 comes down. I'm just going to leave it as 2 times 3. That way, as we continue on, we'll see the pattern of what's happening. So the next term would have been the cubic. That would have been 2 times 3, this would have, I left off my c sub 3. Let me just stick it in there. We have 2 times 3 c sub 3. We have 3 times 4 c sub 4. That would be the next term. That x minus a squared. What's s double prime at 0? Or excuse me, at a? Well, again, all this stuff is going to go away. All we're left with is the 2c2. But what did we want s double prime at a to equal? We want it to match f double prime at a. So finally, we have something other than just the derivative. The c sub 2 needs to be f double prime at a over 2. Let's solve that. Here, c sub 2 from this needs to be f double prime at a over 2. So we've got c naught, c1, c2. And you might start to see what's happening. Every time we differentiate this and then plug in a, everything goes away except for whatever's currently this constant out front. Well, what is the constant out front? In the original one, it's c naught. And then in the next one, it's what would have been the first degree term once it differentiated down to a constant, right? Here, this first term was this thing after it differentiated down to a constant. So what is that first term going to look like when you're at the nth derivative? Let's think about that. So I want the nth derivative, so I'm going to kind of skip ahead here, at a to be the nth derivative of my function at a, right? Just in general. So we could keep going through this process, but what's happening? What's the nth derivative? So this is what we want. So the nth derivative at x, the lead term is going to be what was the nth degree term here after we differentiate down to a constant. But what's happening is the powers are coming down, right? The next one would have been 2 times 3. The next one, 2 times 3 times 4. Then 2 times 3 times 4 times 5. And as we saw before, I think we differentiated some power functions when we were looking at L'Hopital's rule. When you differentiate a polynomial down to a constant, you have first the n comes down, then the n minus 1, then the n minus 2, then the n minus 3. And so that's going to be your lead term, right? You're always left with, at the second derivative, you're left with the second coefficient. At the third derivative, the third coefficient. And with what you have out front is n factorial, right? Here you've got 0 factorial, 1 factorial, 2 factorial, n factorial, plus a bunch of other stuff that I'm not even going to really care about writing out because those are the things that are going to go away when I plug in. All the higher degree terms are going to go away when we plug in a. So the nth derivative at a is just n factorial c sub n. And if you're not quite seeing how that comes out to be a factorial, just take any sort of power term, x to the 5th. Differentiate that down to a constant, you're going to have 5 factorial. So that's really what's happening here. Or if you want, do a few more steps of this. Just keep differentiating, and you can convince yourself that what we're going to have out front is just n factorial c sub n, n factorial c sub n, n factorial c sub n. What do we want this to be? We want this to be the nth derivative at a So that means in general, our coefficients need to be the nth derivative of the function at a over n factorial. And that was our goal, right? We wanted to know what coefficients would make all derivatives match. Those are exactly the coefficients. So that is the Taylor series. So we say, let me switch up colors here for you. We would call this the Taylor series for f of x at x equal a is the sum, 0 to infinity, of c sub n. It's that power series, right? It's a Taylor series is a specific type of power series where the coefficients are this: the nth derivative of the function at a over n factorial x minus a to the n. So given a function and a point, to get the Taylor series, all you're going to need to do is differentiate that function until you see the pattern of the derivatives. The rest of this is just part of the formula, n factorial x minus a to the n. So that is our Taylor series. And then in practice, we'll often use the Taylor series, but when it comes down to approximating, we will stop and use some partial sum. So the partial sums we call the Taylor polynomials. So let's maybe just write this out longhand just to kind of see what it looks like outside of sigma notation. The first term, and you got to think about what does a zero derivative mean. It means you just haven't taken any derivatives, so it's just the function. And 0 factorial is 0, and this thing to the 0 power is 1. So the very first term is just f at a. And then when n is 1, you have the first derivative over 1 factorial, which is 1. So you just have the first derivative at a, x minus a. And then next is the second derivative at a over 2 factorial, x minus a squared, and so on. Third derivative over 3 factorial, fourth derivative over 4 factorial as you go on. And notice I pointed this out a couple of times along the way. If all you did was take the first 2 terms, that's the linearization. If you take the first 3 terms, that's the quadratic approximation. If you take the first 4 terms up to the cubic, that's the cubic approximation. So what you're getting here as you go up higher and higher degrees in this Taylor series, if you stop at the 2nd degree or 3rd degree or 4th degree or 5th degree, you're getting higher and higher degree approximations of the function. And the series just takes that to infinity. So if you stop anywhere along the way, we call that a Taylor polynomial. If you take the entirety all the way to infinity, that's the Taylor series. Next, we'll look at a few of our common functions, and we'll develop what the Taylor series is for those. So what is the Taylor series for the function e to the x, or sine or cosine? So we'll walk through those, and we'll see how you find a Taylor series for a given function. But really it just boils down to trying to figure out this piece, right? The rest of this is just part of the formula. There's nothing to really figure out. You really just got to figure out a pattern of the derivatives of the function.